Okay, so what's a little bit different about this than what we've been doing?
There's no t.
Oh. And what happens when we take the derivative and we don't have that variable, and it's not that specific variable? Like, go back to y. If we took the derivative of y, what do we have to write? dy dx, right? So we've been taking the derivative with respect to x. Related rates, okay? Rate is like a measure of distance over time, right? Or something else over time. We're going to be taking the derivative with respect to t. So I just wanted to go through something real quick before we actually get into what related rates problems are. But if we wanted to take this derivative with respect to t, the derivative of v is 1 dv dt. And then we have 1/3 pi times r squared times h, which is a product. Do you agree? So the derivative of r squared would be 2r dr dt times h plus r squared times derivative of h dh dt. Anytime we're taking the derivative of a variable that's not what the variable we're deriving with respect to, we have to throw in that dy dx. But in this case, since we're taking the derivative with respect to t, we have to call it dh dt, dr dt, dv dt, whatever it may be. Okay, does that make sense? Let me write this here on the board. Some of you are kind of like, I'm not sure which is one. 2y squared plus 2x squared equals 0. If I ask you to take this derivative with respect to x, you would say 4y dy dx plus 4x. Okay? Since we're taking the derivative with respect to x and y is not that variable, we have to apply the chain rule dy dx. Right? On the board, we're taking the derivative with respect to t. I don't see any t's in this equation, right? So anytime we take a derivative, we have to multiply by the chain rule. dv dt, dr dt, dh dt, whatever it may be. Okay? All right, now, we'll get plenty of practice at that because in a related rates problem, we're dealing with rates. It's all going to be with respect to time. All right? So, this is the process in which I would like you to follow when you have a related rates problem. Now, you know you have a related rates problem because they're going to talk about things changing in terms of rates. And I'll show you what I mean in our first problem. But I do expect you to draw a picture. And I expect you to identify any rates of change that we have or we don't have. I expect you to write an equation, find its derivative, and then evaluate using the information that you have identified. Okay. Now, there are a lot of different types of problems we can see, okay? Which is A, why we're spending 3 days on it. B, why you really need to do your homework tonight. That way you can make good use of our time tomorrow, okay? The more problems you get exposed to, the better you're going to feel about them come Friday on our quiz. Okay. So go ahead and read through the first one. What kind of shape are we working with? We are working with a rectangle. And this rectangle, they are describing its length and its width. Do you agree? What would you like to call its length?
L.
L. I'm going to use a cursive L just so it doesn't look like a 1. And what would you like to call the width? W. There's the picture. I need the picture. I know it's a rectangle, and I know you can visualize a rectangle, but it's important for you and for me to see that you've labeled the length as L and the width as W. Okay, because you're going to need to come back to that picture throughout the process. Okay. What do we know? The rectangle is decreasing at a rate of 2 centimeters per second. Anytime you see rate, it is describing what in calculus terms? What's another word for slope? In calculus words?
Rate change.
Okay. In calculus words? Derivative! Okay. You guys are saying all wonderful things, but I just wanted the simple. It's the derivative, right? So, if our rectangle's width is decreasing at a rate of 2, then that means, and then you can put this under your plan, okay? Then that means the W dt is negative 2 centimeters per second. Why is it negative? Because it's decreasing, okay? Its length is decreasing at a rate of 3 centimeters per second. What is that describing?
dl dt.
Okay, in unison. dl dt is, does it say decreasing at a rate of 3?
Yeah.
So negative 3 centimeters per second. Okay. At what rate is the area decreasing when the width is 4 and the length is 5? Okay. So what are we looking for?
After 1 second, how much smaller is the area?
Okay, so in terms of like, if we call the area A, are we looking for A? What are we looking for? The derivative of A. So if I call area A, we are looking for the A dt. When what? W is 4 and L is 5. Okay. Now, we need an equation. An equation that relates area with length and width. A equals?
LW.
Okay, thank you. I'm not saying, some of you are like, well, that's obvious, but you asked us. You gotta be able to come up with it, okay? It may feel obvious, but it may not seem obvious when you're in the middle of a problem, okay? Okay, we've set everything up. We have our equation. Now we need to derive. Okay, the derivative of A with respect to time is dA dt. Okay, LW, what do we need to use there? A product rule. So we have the derivative of L times W plus L times the derivative of W. Okay, so now let's throw in what we know. We are looking for dA dt. dL dt, we said was negative 3. We are looking for dA dt when W is 4. L is 5. And dW dt is negative 2. So what's dA dt? Okay. So the area is decreasing at a rate of 22, what's our label? Centimeters squared per second. Beautiful. Yes.
But if you take the area of it 1 second later, it's not 22 centimeters squared miles.
Well, because you have two different rates happening, right? The rate of your width is different than the rate of your length, so it's not going to be like, it's not going to follow like that linear model that you're trying to think of. Joe, am I making sense?
If it's decreasing at 22 centimeters per second, I'm sure 1 second later it decreases by 22 square centimeters.
Only if the length and width are changing at the same rate. But they are not, so that's not going to happen. Okay? I see what you're trying to say there. Now, some of you may be wondering, well, why couldn't I put 4 and 5 in for L and W right there? Okay? It might not seem quite as, might not be something that you wanted to do right away in this problem because it's a little like the derivative would be 0, it's not changing at all. We know that's not true. Okay? But we cannot plug in any constants to variables that are changing. Since the length and the width are changing, we have to take the derivative first, then we can plug in numbers. Now, if it said the length was not changing, then we could plug that number in right away and be fine. But if something is changing, we have to take the derivative and think about the rate that it's changing before we can plug in any numbers. Okay. Let's go ahead and look at the next one. Go ahead and read through it. What kind of shape is going to help us with this? A right triangle. Good job. Okay. So we have two cars leaving, one traveling north and one traveling east.
Right.
Okay. At first I panicked like I needed to go the other way, but okay. What is the distance between them changing? So let's go ahead. What do you want to call car 1? A. What do you want to call car B?
X. B.
I said car B. I meant car 2. But we're going to call it B because that's what we do. And then we're going to talk about the distance between them changing. D for distance. I think that makes sense to me. Okay? Anytime they say distance, I'm usually going to put a D. Okay. Let's talk about our plan. What do we know?
Car A is traveling north at 30 miles.
Okay, 30 miles per hour. What did they give us? Did they give us A?
Oh. Oh, they didn't.
What did they give us? They gave us dAdt. They gave us a rate, right? Miles per hour, that's a rate. So they gave us dAdt. And they gave us dBdt. 40 miles per hour. Okay? How fast is the distance between them changing after 5 minutes? Are we looking for D? We are looking for dBdt. Ugh. We are looking for dBdt when time is 5 minutes. Okay, so I have a question. Our rates are in miles per hour. Our time is in minutes. Multiply what by 60?
30 and 40.
So you would like to change our rates to miles per minute?
Yes.
Is everyone okay with that?
Then we divide by 60.
Wait.
Because if you
Oh,
multiply
yeah.
by 60, then we
Okay. That's okay. We'll get there down. So we want to divide by 60, right? Okay. So this would then be 0.5 miles per minute. And what? Oh, 2/3, right? And 2/3 miles per minute. So maybe I'll make that 1/2. Okay? See what we're doing here? We have to have consistent labels. So hours, minutes, that's not okay in one equation. So now everything is in terms of minutes. Okay. Here we go. What equation can relate A, B, and D? Pythagorean theorem. A squared plus B squared equals, in this case, D squared. Right? That looks a little awkward. Okay. Now, are all of these changing? Yes, which means we have to take the derivative as is. So we have 2A dA dt plus 2B dB dt equals 2D dD dt. Okay. Now, you wouldn't have to do this, but I think this could save us some calculating later. I'm going to divide both sides by 2. Is that okay with everyone? It's not going well for me. There we go. Okay, and let's talk about what we know. We know that dA dt is 1/2, and we know that dB dt is 2/3. We're looking for dD dt. What? Okay, can you be more specific than plugging in all the numbers?
Well, if you calculate each side of the triangle, A and B using the rate times 5 minutes and B using Pythagorean theorem.
Okay.
Plug in all the numbers and then divide B out to one side to get dB dt.
Okay, so we know that our time is 5 minutes. Well, there's nowhere to plug in time, right? But we have some rates. And how do we find distances? Distance equals rate times time. So if we want to know how far we are in car A, we're going to take our time, 5 minutes, times our rate, which is 1/2 mile per minute. So what is that? 5 minutes. Okay. B. Our time is 5 minutes times our rate, 2/3. 10/3. Okay. Now we have to figure out what D is. Well, we know the Pythagorean theorem is A squared plus B squared equals hypotenuse squared. Okay. So with your calculators, figure out what D is so we can plug that in. Do you get 25/6? Okay. Okay. So now if you add these two, divide by 25/6, I'll just save you some time. It's 5/6. So the distance between them is increasing or decreasing? Increasing, because we have a positive rate at 5-6 miles per minute or 50 miles per hour. If you go ahead and change that back to miles per hour if you wanted to. Okay, so in this one, we had all the information, but we had to do a little bit of calculating on the side. Okay. Now, I would say that example one, yes.
Is it just coincidence that it's like the Pythagorean triple 3, 4, 5, like 30, 40, 50? Like, would that be able to shortcut everything and you'd be like, oh, it's going to change at 50 miles per hour because the length is changing it, or like one of them is changing at 30 and the other is changing at 40, so that diagonal would be 50.
You know, I am not sure the answer to that question.
Okay.
It is suspicious. I agree. I wonder if it just specifically, because it's really about like that 5 minutes, right? If we found a different time, it wouldn't be 50. And so I think that this problem shows a nice time value to get you a nice number that just happens to be that Pythagorean triple. But if I were to ask you about 10 minutes, it wouldn't be that.
Okay.
Does that make sense?
Yeah.
Okay. All right. Now, example one and example two, I would say are fairly simple problems. But do you see how differently we went through them? Right? More problems we can do, the better. Okay. Let's go to the next one. Read through it, please. Well, this one's kind of nice, right? Because it gave you some information about S, right? Okay, and we have our picture. So picture's done. What do we know? Do we know any rates? Okay, so if S equals 50t squared, then technically we do know ds dt. Do you agree? So we do know that ds dt would be 100t. Okay, what are we looking for? We are looking for the change of the angle, right? So since our angle is theta, we are looking for d theta dt. When time is 10. Okay. What equation can relate theta s in 2000? Say it louder. Tangent, you betcha. The tangent of theta is s over 2000. Okay, now I'm writing a number. You haven't seen me do that yet. Why can I write 2000 in this equation? Because it's constant. It does not change, okay? The camera, that's going to change as it follows the rocket. The rocket, it's shooting up in the air. Its distance is changing over time. The angle is changing over time. But that distance the camera is horizontally from the rocket, as long as it shoots straight up, that's never going to change. So right away, we can put that in our equation, and we don't have to worry about that third variable, okay? Because it's constant, okay? Now, this is exciting. We get to take this derivative, okay? What is the derivative of tangent? Okay, so we have secant squared theta, but we're taking the derivative with respect to time, so we have to multiply by d theta dt. Okay, don't get too out of control with the derivative of s over 2000. That's basically 1 over 2000 times s. So we have 1 over 2000 times ds dt, the derivative of s with respect to time. Okay, now there are a couple different ways we can do this problem. Okay, I'm going to make my picture a little bit bigger. Can't do it. Okay. So we're looking for d theta dt. That's good. ds dt. We know ds dt, correct? We know ds dt is 100t. And we're looking for when time is 10. So what's ds dt? Okay. Now, we're looking for d theta dt. Our issue becomes secant squared theta. All right? Do we know what theta is?
No, but you can calculate.
We can calculate it. Now, there's a couple different ways we can do it. You could either figure out what the angle is with your calculator, or you could use the trig relationships. Okay? You all know how to use your calculator, so I'm not going to show you that method. But I'm just going to remind you of our simple trig relationships. Okay? When t is 10, what is s? It would be 50 times 10 squared, which is what? Okay, so what's this side? 50,000? 5,000? Could we find the hypotenuse if we have 5,000 and 2,000 as legs? Yeah. Well, what's 2 squared? And what is 5 squared? Okay, so this would be 290,000. Right? Agree with that? Square root of 2, or do I have too many zeros? Do I have the right number of zeros?
It's
Too little? How many more do I need? 2 more? So that comma is going to turn into a 0. 0. That? Is that good enough? Yeah. Okay. So, like Joe said, yes, you can use your calculator and figure out the radian value of theta to find secant squared theta. Or we know that the secant relationship is hypotenuse over adjacent. So, secant squared is just hypotenuse over adjacent squared. Okay, now we're using our calculators. Okay, so it's not like that way saves us from like a non-calculator kind of problem, but I just want you to be aware that you can do that and it saves you some rounding error, okay? So now we can solve for d theta dt. Basically have 1/2, and then we're going to divide over that big ugly fraction of secant squared. You should be getting 0.069. So now let me know. So, are you getting 0.069? Yes. 1, 2, 3, 4, 5, 6. Okay. What is our label? We know things are changing per second because they gave us time as 10 seconds, but it's an angle.
degrees per second.
We're going to have to do radians. We always want to do radians. Okay, you always want to do radians. So, our answer is that the angle is increasing at 0.069 radians per second. Okay. So before we move to the next example, what are some words that jump out at you to tell you that we're working with a related rate problem? Like, what are some things that have stuck out to you? Okay, you get some sort of measurement that's a rate, right? It might not say the word rate, but we've seen centimeters per second, miles per hour. This one said the rate, this one actually said rate, right? Rate of change of the angle, okay? So sometimes it's going to be obvious. It says the word rate. Or you're going to have to infer because they give you numbers that are in terms of a rate, okay? So I think this is going to be our last problem. This might be one of the more important problems. You will see cone problems often, okay? go ahead and read through it. We have a cone. Well, we have a pile of sand in the shape of a cone, do you agree? And as they pour the sand, you can even like imagine it, right? As you pour sand, the pile's getting bigger, right? Okay, so we know that we have radius and height, a part of our cone. Okay? So what information do we know? We know dVdt is what? Per what was it? Per minute.
Cubic feet.
You said feet. I didn't write that down. Okay. Cubic feet per minute. Okay? Because the volume is changing, we have dV dt. Because we have the rate of the volume. Okay? What else do we know? R is equal to H. Okay? Anything else?
That means the base is equal to,
What did you say?
that the diameter of the base is equal to.
Okay. We know if R equals H, then the diameter would be 2H. Yes? Basically, that's all of the given information, though, right? So we need to find dH dt when our volume is 1,000. I don't know why I want centimeters so much. Cubic feet. Okay, this is probably something you're going to want to remember. Volume equals 1/3 pi r squared h. That's the volume of a cone. It is. It is. Okay, that's the equation I showed at the very beginning. Okay, now let's maybe flash back to that, Trevor. Okay. So you're going to get cone problems often in this unit. I'm just going to tell you that. Okay? So it's important that you know this. Now, look, when we took this derivative, and I don't want you to write this down, we had dV dt, we had R dr dt, H, and dH dt. We don't know anywhere close to that amount of information. dV dt, V, dr dt, R, dH dt, H. That's 6 different things, and we need to know 5 of them to solve for the 1. Okay? Sometimes you're going to get information about R and H and their rates. Sometimes you won't have enough information. We know nothing about dr dt, and we know nothing about dH dt. But what do we know? R equals H. Okay, so what we can do, since we want to know the rate of the height, we can change everything to be in terms of H. So since R equals H, we can write volume equals 1/3 pi H cubed. That way, we don't have to worry about the RDT or R because we know it's the same as H. Okay? I'll tell you, sometimes they'll give you a ratio. Like, well, the radius is 8 when the height is 7. And so then you might have to plug in a ratio of R to H to do this. Okay, here we have a 1-to-1 ratio, so we can just plug in R for H. This makes the derivative a lot better, doesn't it? Yeah. dV dt is pi h squared dh dt. We do the power rule, the 1/3 times 3 will cancel out, right? Okay. Now, we know that dv dt is 10, don't we? And we are looking for the h dt, but oh boy, we don't know h. Or do we? Okay, so sometimes we're given some information and we have to use that to find other things about our problem, okay? So we have that the volume is 1,000 feet. And right here, we know that the volume, cubic feet, excuse me, is 1,000. And that it should equal 1/3 pi h cubed. So we could multiply by 3, divide by pi, and then cube root it to solve for h. Okay, that is a terribly ugly number, I get it. Some of you are going to put it in your calculator. That's fine. Some of you are going to substitute it like this. Here is my warning. If you're going to put it in your calculator, you want to be able to call that number back up. So either use the store feature in your calculator or arrow back up and call it down. Okay? Do you guys remember how to use that store feature in your calculator? Vaguely. Should we talk about it real quick? Okay. Okay, so we have the cubed root of 3,000 divided by pi. Okay, and it's that weird 9.8 number, right? So remember this STO arrow, that's your store button. I could like store that in alpha A. Okay, so then what I can do is when we go to solve this equation, I need to take 10 divided by the quantity, so parentheses, pi times that alpha, whoops, sorry, 10 divided by the quantity pi times alpha A.
Is it supposed to be squared?
Baloney. Yes, it is supposed to be squared. I wondered why. Better? Okay, squared. So that gives us that dH dt is 0.033. What's our label? We're talking about a linear height, so just feet per minute. Volume was cubic feet per minute. Area would be square feet per minute. Height, length, width, regular feet. Okay, linear feet. Okay. Now, you don't have to use the store feature in your calculator, but you better be able to get to 0.033 without rounding errors. Okay? If you round that to 9.847, you are not going to get 0.033 in the end. I can almost guarantee it. Okay, looking at your homework, you have 8 total problems, 6 of which are bolded and underlined. Now 6 problems, okay? We very slowly went through 4, okay? We went pretty slow, okay? The first couple problems will be more of the simple ones, okay? And they'll just get progressively a little bit more intense, okay? I will tell you that tomorrow, all day, we're going to spend doing these problems, okay? I'm going to force you to get outside of your comfort zone a little bit, all right? I am going to push you tomorrow. So if you come into tomorrow without having done any of the homework, it's going to be very, very rough for you, okay?